Normally when you perform an experiment, you have to apply a real magnetic field to split the energy lines. Now the energy line is split, so we say that there's as if there is a pseudo-magnetic field. It's a pseudo. There's no real magnetic field. Okay. It's a pseudo-magnetic field.
All right. Other question?
As you know, in graphene oxide, a lot of oxygen functional group is there. For catalytic activity, only carboxylic helping the catalytic activity, or what about the other functional group, oxygen functional?
I think from most of the reaction I've tested, the carboxylic group is the most effective because it can act as an acid catalyst. I mean, although there's all kinds of oxygen functional group, the one that's most acidic is the carboxylic group, right? Because the hydroxy group, epoxy group, they're not so acidic in character. So for catalysis that requires an acidic function, like when you react with a base, this is the best. It's the best group. But the other oxygen functional group may be useful in some other reactions I couldn't comment. But I can comment that whenever you have that carboxylic group, it's better than not having it.
Other question? Yes.
Have you done an experiment regarding the at what point do you see that the bubble will burst? I mean, the graphene bubble
yes.
will burst.
If you heat up the bubbles to, in this case, about 1,000 degrees Celsius, it bursts. Because I think the trap, whatever that's trapped inside the gas, is too high, the pressure, and then it bursts, and then it forms a nice hole. It forms like a hexagonal hole, like an anti-dot. Yeah.
And just a follow-up question on because you said that it will create a supercritical fluid inside the bubbles, and it will etch the diamond.
Yeah.
Why it will not etch the graphene?
Yeah, that's a very interesting question. That's a very good question. So, this graphene, the in-plane sp2 bonding, where I showed just now that when you form this kind of a structure, you have a concave, convex side. The electron distribution is more on the outside. That's what I believe. I do not know actually. The electron distribution is more on the outside. Inside is less. So outside is reactive, but inside is less reactive than the flat graphene. I believe that all the electrons go there, and somehow it is stronger than the diamond for this reason. At least this proves that it's stronger than diamond. I believe it's because of this asymmetrical distribution of electrons inside and outside that reduce the chemical reactivity of this concave part of this graphene bubble.
Also follow up this question. The water trapped inside the nanobubble.
Yes.
You demonstrate supercritical fluid above the critical temperature, right?
Yeah.
Have you also looked at the lower temperature side? For example, one of our colleagues has demonstrated that water at such a confined space can be super cooled significantly.
Oh, I see. No, I'm not. I think it will transform to ice once I cool down. It become ice.
And then they demonstrate that even 30 or 40 degrees below zero, it still remain liquid phase.
Oh, it's still liquid
Yeah,
phase.
at a confined state. Yeah.
Interesting experiment.
You probably should take a look.
Okay. So you mean it starts to freeze? Even we can see from hydrogen bonding if it already starts. It's probably true because there are some literature reports to say that if you take 2 pieces of graphene and you confine a water layer, they form ice very easily, even at room temperature. Yeah.
Okay. Final last question. I think it's quite an experience to see how Professor Low demonstrate all the experiment. Originally, I think most of the students here are more physics oriented. You try to do the perfect crystal, the perfect graphene. Now we discovered that a more defective graphene will be even more useful.
Not generically true, only for some limited examples. Because it's so difficult to grow perfect graphene.
And the other comment I need to make is originally, most of us, when we show our CV, look at how many 100 papers, how many tens of JACs he has published. But now Professor Low doesn't need that. He just shows 10 Nature series papers. They will tell everything. So let's thank Professor Low again.